Yes, sir. Shall we start, sir?
Yes, yes. Can you hear me well?
Yes, sir. Yes, sir. Your audio is clear, sir. So we will start the session, sir. So participants one by they will join one by one, sir. One by one.
Okay.
Okay, madam.
Yes, sir.
Yes, ma'am.
Yes, ma'am.
Yes, sir.
Good evening to one and all present here. I'm delighted in welcoming you all for this Day 10 session of 2 weeks International Faculty Development Program organized by Department of Computer Science and Applications, SRM Institute of Science and Technology, Ramapuram campus. Now, I invite Dr. J. Dileepan, Head of the Department and Vice Principal Admin, for delivering the welcome address.
Thank you, madam. Good evening to one and all. I extend a cordial welcome to you all to Day 10 of this 2 weeks online international faculty development program. First, I would like to extend my hearty welcome to our chief guest, Professor Rama Sellappa, Bloomberg Distinguished Professor, Departments of Biomedical Engineering, School of Medicine, and Electrical and Computer Engineering, Whiting School of Engineering, Johns Hopkins University, Baltimore, Maryland, USA, with a deep appreciation for accepting our invitation in spite of his busy schedule. Your presence makes us very happy, Professor. Thanks for joining us today. The topic of the today's session is design a fair, robust, and interpretable AI systems. As you are aware that artificial intelligence is paving a way for new ways to enhance people's lives all across the world, from business to healthcare to education. It also raises additional concerns regarding how to best include fairness, interpretability, privacy, and security into these systems. So fairness is highly connected to the AI models, interpretability, and transparency of the process with which those models were created. So our chief guest of the today's session is very much specialist in this domain, and I am sure that the today's session will be an eye-opening session for all the participants. So once again, I welcome you all to this wonderful session. Thank you.
Thank you, sir, for your welcome address. Now I call upon Mr. D. Rajkumar, Assistant Professor, MC Department, for introducing our guest to the audience.
Good evening, everyone. It is my immense pleasure to introduce our resource person of the day, Professor Ramachellappa. Professor Ramachellappa is a Bloomberg Distinguished Professor in the Department of Electrical and Computer Engineering, Whiting School of Engineering and Biomedical Engineering, School of Medicine at St. Johns Hopkins University. Before joining Johns Hopkins University in August 2020, he was a distinguished university professor in the ECE department, University of Maryland, Institute Advanced Computer Studies at the University of Maryland. At UMD, he was also affiliated with the Center for Automation Research and the Department of Computer Science. Professor Ramachellappa received his Bachelor of Engineering honors degree in Electronics and Communication Engineering from the College of Engineering, Guindy in 1975, and ME with distinction from Indian Institute of Science, Bangalore, India in 1977. He received his MS in Electrical Engineering and his PhD in Electrical Engineering from Purdue University, West Lafayette, in 1978 and 1981, respectively. His current research interests span many areas in image processing, computer vision, and machine learning. Professor Ramachellappa is a recipient of several awards, including NSF Presidential Young Investigator Award. He has received 4 IBM Faculty Development Awards, Jack S. Kilby Medal for Signal Processing from the IEEE, KSFU Prize from the International Association of Patent Recognition. He has also received awards like Technical Achievement and Meritorious Service Award from IEEE Signal Processing Society. He has also received Inaugural Leadership Award from IEEE Biometrics Council, and he is also an distinguished alumni recipient of Distinguished Alumni Award from Indian Institute of Science in 2016. He has also served as a general and technical program chair and co-chair for several IEEE international national conferences and workshops. He is a Golden Core member of the IEEE Computer Society and served as a distinguished lecturer of the IEEE Signal Processing Society and as a president of IEEE Biometrics Council. He is a fellow of AAAI, AAAS, ACM, IAPR, OSA, and NAI, and he holds 8 patents. Sir, we are extremely delighted to have you in our midst. Now we request you to take over the session. Thank you, sir.
Thank you for that warm introduction. I hope you all can hear me well. I'm going to share my slides. And so, Dr. Dileepan, as I said in my email, sometimes Zoom links fail.
Yes,
so
sir. Yes, sir. Yes, sir.
monitoring and
Yes, sir.
hopefully-
Yes, sir.
Yeah, thank you.
Okay. Okay, sir.
All right, let's see. Let me share my. So are you seeing my slides?
Yes, sir. Yes, sir.
Okay. All right. I'm glad to be here. The date is not correct. It should have been July, I guess, 21st. But anyway, I'm going to be talking about unbiased, robust, and interpretable AI systems and design of such systems. And I'll take 2 examples as we go through the issues. So the outline of my talk is, of course, I took my first course in AI in spring of 1978. And that was the time when AI was actually having difficulties, the so-called AI winters. Because the thing about AI is that everybody promises too much, okay? And sometimes it doesn't deliver what everybody thinks it should do. For example, just a couple of years ago, everybody thought the self-driving car should be on the streets. And it's kind of there, but it's mostly not there, right? So there are always very high expectations because artificial intelligence seems to excite something in us. We say, oh my goodness, so we can actually create a system that can behave like humans and work like humans, interact with humans, and so on. So I know it has gone up and down, up and down. So I'm going to very briefly show a timeline as what happened with AI and ask the rhetorical question, will AI winters return? And I don't think so. I hope not. But who knows? Future is hard to predict. And then I will talk about 2 cases that illustrate some of the issues that are coming to the forefront these days. Robustness. Are they robust to adversarial attacks? Since most AI systems are now designed using data, how you collect data becomes important. Privacy is critical, as well as bias in data, because you don't want AI algorithms to kind of favor one group of people versus the other. So that is of consequence. And then we also, have moved to a black box approach now, right? The interesting thing is, when neural networks became popular in the mid 80s, 1986, because of Hopfield network in 1982, AI and neural networks were not in much of love with each other, right? In fact, the idea that you would just send a data into a black box and get some answers out of it was not appealing to traditional AI folks, computer vision folks, and so on. So I'm saying that before deep learning came, AI was interpretable, right? Rule-based systems, regression models, logistic regression models, SVMs, k-nearest neighbors, all of these classical machine learning techniques were interpretable. Bayes networks, for example, because we do understand the conditional structure of Bayes nets and so on. So when we went to this, deep learning thing, it suddenly became like not interpretable. So people are now asking the question, why is this box doing what it is doing, right? So we should be able to explain. So I'm going to, discuss these issues in the context of 2 problems we are working on. So very quickly, of course, everybody knows about the Imitation Game, the movie, and Alan Turing. So if you look at the history, we have had lots of interesting developments, right? Theorem proving was big in the 50s and 60s. Heuristic search, the A-star search algorithm, everyone knows. And they were all kind of set in the context of winning games, board games, chess, AlphaGo, et cetera. And then symbolic processing was the flavor in those days. But even then, people worried about how to incorporate common sense reasoning that humans are mostly good at. And then many application areas developed. One is natural language processing, which still is one of a key application area for AI, as well as computer vision and robotics. And of course, expert systems came and went, and so on. So, this is just a one slide view of AI. Of course, if you like to read more about it, the book by Stuart Russell and Peter Narvik is definitely a place to go to. Of course, we have a lot of techniques, symbolic techniques, things done through analogy. Right in the mid-80s, Professor Julia Pearl brought Bayesian inference, and so Bayes networks took off. And then there's evolutionary computations, connectionist methodologies, and so on. So just below that in the red boxes, I have listed various well-known algorithms. Some of them are still active. Of course, clustering, unsupervised learning, representation learning is there. Reinforcement learning is very much at play when you are dealing with, continually improving yourself, and so on. So you can also see some of the applications that are listed here, right? So as I said before, when AI was working, well, everybody always expected it to do more, okay? And there was a report, Lytle report in the UK in the mid-70s that cast doubts on viability of AI, and then, AI funding kind of dried up, and then it came back again in the mid-80s. So AI has this, seesaw life to it. Okay, so right now, what could make AI winter come back again? I think face recognition is one of the application areas in computer vision that's showing the power of data-driven inference. Of course, immediately it has also raised concerns whether it would work well for people across gender, across skin tone, and so on, right? So bias and fairness have now come up as key issues to worry about. And deep learning are very susceptible to adversarial attacks, even though there are two visually indistinguishable images. If you send them through a deep learning network, they could really map to totally different labels. So, this came about in 2013. Although those of us who have worked with statistical inference are not entirely surprised that even small outliers can create havoc. I mean, it's been known in time series literature going back to the mid-70s. So, we need to worry about robustifying all the so-called deep learning systems, and interpretability is again moving away from black box, right? So let me just quickly give you a couple of examples. Okay. We did some work on neural networks between 1986 and 1996, and then SVM came and we kind of dropped it. And so right around 2014, we had a major project from IARPA. It's called Janus program, and it had very tough metrics. Basically, it's unconstrained face verification, identification, search, et cetera, et cetera. So I was at University of Maryland at the time, so I was a lead, and we have all those other universities mentioned here as partners. So the goal was to build the best face matcher at that time. And obviously 2012, changed our, landscape. AlexNet, one of Professor Jeff Hinton's students showed a simple extension of LeNet from Jan LeCun that was there to be picked up. Added some layers and replaced sigmoid nonlinearities with ReLU restricted linear units, and brought in GPUs and so on, and showed that when this network was applied for ImageNet challenge, it performed better than traditional handcrafted computer vision features. So I like to say computer vision field has just totally changed. So if you go to any of our conferences, it's all about deep learning, right? Because we used to, in the 80s and 90s, worry about geometry, illumination models, scene models, context, and all of that. Now they're all kind of gone. Although some people want to still, bring that back and combine it with data-driven methods, but it's pretty much deep learning is ruling right now. So we thought, okay, we'll give it a shot, right? So we designed multiple approaches. We introduced multitask learning in the context of deep learning, fusion of networks, and so forth. So we were able to build a state-of-the-art face recognition system in just a matter of years, and 4 years it took, and then it's being used widely and so on. So since this data was collected in a careful way, even when building as part of the program, so we were able to avoid many of the issues. So if you look at a traditional face recognition system, you have the detect faces, and then you have to extract fiducial points, align them, because people are not always looking at the camera, and then you develop representations and match them. So this is a generic setup for face matching. So we built a multitask network. Basically, what happens is there are so many different tasks you have to do, right? You have to detect the face, and then you have to be able to extract fiducials, and then figure out which fiducial points are visible, and then estimate the pose of the face so that you can align them and create a frontal looking face, and so on. So these are different tasks, and not all of them have the same amount of training data. It's very easy to ask an Amazon Turker to put a box around the face. So you can create a lot of training data, annotated training data. But if you want them to mark the fiducial points, it's cumbersome, and oftentimes it's erroneous. Likewise, accurately estimating the pose, roll, pitch, and yaw is also difficult. So you will have here multiple tasks, but different tasks have different levels of training data. So when you build a deep network, what happens is at the bottom layers, the features are somewhat generic, Gibar-like features and so on. But as you move up the level, like ResNet 101 or 151, they become more specific to the individual tasks that are assigned to them. So here you can have Euclidean loss function for fiducial and for pose estimation, because they're kind of like regression problems. Whereas you will have a classification, cross entropy loss or whatever for detection, gender, face detection, and so on. So here you have various examples where the blue box indicates where the face is located. The green dots indicate the fiducial points we need for alignment. The red things, which are hard to read, indicate the pose. And if you are enrolled in our library, gallery, we will tell you who you are. For these are famous people, right? So it turned out we can't just do it with a single network. So we kind of, built multiple networks, the different loss functions and so forth. And there are data sets that were available at the time. It's still available. MS Microsoft 1 million data set, a little noisy. So we had to apply a, apply a clustering technique to curate it. And that's always going to be an issue. And we also collected our own data set, and making sure that we only use people's faces that are in the public domain. No privacy. Privacy was completely followed, right? That's very important, because we didn't want to design a system and then somebody come and question how we got the data. So this has to be above board and so forth. So that's one of the things we learned early on. And then we also had videos, right? There are two sets of data sets. By the way, if you want to evaluate your algorithms, these data sets are publicly available, not CS6, but IJBB and IJBC. These are available for you to try and so on. You have to talk to somebody at NIST, I guess, to download them. We do single frame based face recognition. You also do video. Well, some would say, oh, when you have video, you have a lot of data. But usually the faces are small in videos, unless it's a newscast, news people. So here you have in IJBB a person with the green box. We call him, the target. So we have to figure out where he is in multiple shots. It's not a single video, so you really can't track him. You have to detect and associate. That's a new thing, right? If it's a single video, you can track a person, but if the person changes, outside a restaurant, inside an office, and somewhere here and there, you lose the track. So you have to be able to associate, and that can become complicated. So here we have the single shot surveillance video and so forth. So it's a very tough data set, but deep learning, everybody, traditional people are sometimes unhappy that one methodology has taken over the field in computer vision, in language processing, etc. So I call it the good, the bad, and the ugly of deep learning. The good is the performance. It really works well if you have the right kind of data. Basically, if the mapping between data and labels is unambiguous, then you just go and build a deep network with enough data. It seems to be working well. For example, here we are looking at 10⁻⁻⁶ false alarm, false acceptance rate, and 80, 85%, 95%, and so on. We never thought when we started the program that we would reach this level of performance, right? So, and what is the bad and the ugly part? Bias and privacy, right? So you have that. And then CS infinity is a much, much harder problem. It's the surveillance kinds of things. And you can see how many subjects we have, right? Several thousands, hundreds of thousands of subjects and so forth, okay? So this became a hot area. By 2017, 2018, we were able to build a robust system and all of that. So you could see, I mean, I can show you more of these things, but it was not always giving 90%. If you have surveillance to single, that means I have a video, I detect a person, and I have a single copy of that person's face in my library or gallery. So it's about 70% top rank, right? Not enough to deploy. So the problem is not completely solved, right? If you have difficult cases, it's a problem. Now, what happened was companies got it. Microsoft, IBM, Amazon built a recognition software. So somebody at MIT, Dr. Bolavini, did an experiment. She collected this data set called PPV, where white male from Netherlands and dark-skinned men and women from Africa. These were, the faces from Africa belong to politicians, news people, and so forth. So she also had the light-skinned females. As you can see here, the error rate, with some of the systems was pretty high, right? You can see 34.5 error rate and so on. So this created a lot of anxiety. Of course, Amazon went back and fixed some issues with the data set bias and so on, and brought the error down about 6% or something like that. But still, this got a lot of attention. Okay, so immediately it raises the question: if so if you look at another data set that's around for skin tone and so on, as you can see, the Caucasian representation is very strong. Okay, so if you build a deep learning system with such a bias, okay, thank you. Then your system is going to do what it learned well. Everybody says, oh, deep learning, it has issues. That's true, but we provide the machines with data, right? We provide the machines with data. Just like when we built Bayes nets, we designed the conditional structures. There's something known as deseparation in the design of Bayes networks, which kinds of makes sure the conditional probability structures are all good. So if we don't do it right, the thing is going to learn that that's not quite right. Okay, so that is one of the points. We just have this issue of bias in face recognition. So as you can see here, Amazon recognition in 2018, it had certain performance, and then it got better. It became green, right? But still, the damage was done. It raised an issue that deep learning, and these days AI and deep learning are kind of all in this together, right? In fact, in the late 70s, 80s, and so on, AI was kind of by itself. You have to know Lisp, and then you have to be trained in symbolic reasoning and things like that. Now, pretty much everything is kind of coming under AI, machine learning, AI, SVM, everything is kind of all in a big basket. So, but deep learning has created similar short hair and so forth. Women with short hair were often classified sequences if a police department or somebody is using your system, and if they wrongfully match some, it creates problems, right? And such things have happened. So that's why people are worried if AI true. People are using deep learning methods and other machine learning methods for looking for cancerous cells in mammograms, or diagnosing diabetic retinopathy, or early detection of low blood pressure situations when somebody is under anesthesia, or sepsis, alerts and so on. So we have to make sure that the methods we build are fair. Again, the question of fairness is becoming very interesting. If you look at some recent survey papers, there are at least 23 different ways bias can creep in, and there are 20 different metrics for defining fairness, and it's also task dependent, right? So, it's still an area that's being worked at. So what we did was we were also concerned that when we do face recognition, we need to know what the deep features code. So we did some work, which we published last year in the annual Face and Gestures conference, where we wanted to come up with a metric to figure out, in addition to ID, when we design face recognition, we have ID, what other things are represented in the deep features. To our surprise, gender was very much expressed in these features. Pose was expressed, age was expressed. So here, crystal face is from our group. You can see we were looking at mutual entropy. It's called MINE. It's an approximation to mutual entropy of how much of gender is represented in the deep features, how much of identity, age, and so on. As you can see, when you move up the levels in a ResNet, ID is somewhat low, expressed, not much till you reach the final, fully connected layer, because that's when we force the network to learn the ID. Whereas if you look at gender, it is prominent early on, and then it goes down, and then age seems to hang around. So we figured out there may be networks that we built. There are lots of different networks for faces. Each one of them may code these covariates differently. And this may be one of the reasons why we have bias in face recognition, right, towards dark-skinned men and women. If the gender is very strongly expressed, then it has a gender bias and so forth. Okay, later on, I will show in a traffic cam problem, the data also becomes biased to a particular camera. If you have multiple cameras, and if you use data from one camera, then it kind of gets used to that. I know, because it's data driven. Okay, so there's no two ways about it. So we did all of that, and we looked at various ResNets, and ResNet v2, the inception network from Google, and so on, and we saw similar behavior. And so the key takeaways are, face recognition features implicitly encode. Not all do, some do. Okay, ours expresses gender a little bit more, because we included gender information in the early stages when I talked about multitasking, because we thought that might be useful, but that introduces bias. Whereas if you look at the ARC face from Imperial College, they have a separate detection. They didn't combine it with gender and so on. So it has less of a gender expression, therefore less bias. So we found this. So once you have, okay, then for face recognition, you can identify these covariates, right? So you understand where the bias comes from. But if you're doing object detection, object recognition, you may look for bias towards camera views. You may look for bias because of material properties, et cetera, et cetera. So each task will have certain subtle things, that could alter its performance. So that's what you have to figure out and remove them. But one of the things that happens is when you remove bias, sometimes performance goes down. So here we have the trade-off, right? You want to be unbiased, you want to be fair, but performance may come down because sometimes you may have to remove some data from your training data set, or you have to collect more, balanced data set and so forth. So, you have to decide what is, how much of a bias you are willing to tolerate. Most people would say, I want totally unbiased system. Well, if the performance is very low with that as the criterion, then, it's not going to be useful, right? So we have to, as you know, in hypothesis testing, we always worry about type 1 error, type 2 error, and which is more critical, right? In Neyman-Pearson lemma, we worry about one kind of error and we keep it under certain limit and minimize the other error and so forth. So life is, in all decision making situations, you got to balance out these conflicting things. So we designed a system. As a precursor of this is called Agenda, which is an archive. So basically, we take any in the bias removal thing. There are two ways you can go about it. As you build a system, you can watch for these things and make sure you do it properly in terms of collecting data sets and things like that. Or once you have done building and then you say, oh my God, this thing is biased, what do I do? That's called post hoc processing, right? So here we are in a situation where we already built a super network in 2017, and then we are worried about the bias. So we go and try to fix it. So we create an adversarial loss function to reduce bias. So here we have set up a block diagram where we start with the pre-trained network, and then we create data sets using a model from the features. We feed it in, and we have a discrimination loss. We have an adversarial loss function to minimize the bias. As you know, fairness methods, I will refer you to our archive paper for more details on that. It all comes to finding the right loss function. As you can see in deep learning papers these days, sometimes you have about 5 components in a loss function, because when you are restoring a bad image, you have to make sure it's perceptually good, and then you want to make sure you want to be able to de-blur the algorithm, and you want to preserve this, preserve that, preserve semantics. And so you start adding these loss functions, and every one of them has a parameter. This is too many hyperparameters, that are there to galore it, to fix them, right? So you can actually, once you know what the bias is, you can improve the gender bias. Here, we define bias as a performance, male to male performance minus, female to female performance, right? If you compare 2 male faces, if you do much better than when you compare 2 female faces, then obviously, you are biased. So here we have a whole bunch of plots here, and by doing an adversarial loss-based bias reduction thing, we can move the performance up, as you can see in the red at the other color right here. Okay, so you can see that these are good performance at 10 power minus 5. As I said before deep learning, we were always operating here because we couldn't really go into these regions. So that's why people like to do deep learning, but you have to worry about similar things we are seeing for skin tone. Unfortunately, for skin tone issues, we don't have a lot of training data to kind of understand the bias issues and so forth. There's just one data set called BPPT or something like that. And so we use that. Okay, now I talked about the bias performance trade-off. So here is the true positive rate, difference, right? Bias, and then there is a term for bias. There is a term for performance. So you can now create this bias performance trade-off. This is going to be different for different tasks. What is bias for phase is different from what is bias in medicine, right? What is bias in other issues? Okay, so you have to kind of be a domain expert to do that. Okay, now, so here we are comparing, gender bias analysis, crystal phase analysis, and so forth. As you can see, we have the various performances, 80% performance with the pass, which is our algorithm, and we can have bias with respect to hair. We can, look at the 10 power minus 5. When there is less bias, performance goes down, but not by much. Other thing we wanted to do was right around 2015 itself, Antonio Torralba at MIT was looking at this issue of attention maps. Where exactly the deep learning is learning it, wherever it's learning from, right? Now, in the case of computer vision, we have for long worried about salience detection. Suppose if I give you an image, what interests you? Where do you look? Is there a person with a 6 feet nose? Salience detection. So it's kind of an unsupervised one. It just jumps out of the picture, okay? So we wanted to find out what our networks do when we present pictures of male and female, dark skin tone, light skin tone, okay? When we look at it, as you can see, in the case of female, I mean, you can, there are various methods with neural networks. CAM, class activation map that came from Torralba's group, and then Devi Parikh and others talked about grad CAM by introducing gradients in this calculation. Basically, they all come out of the backpropagation algorithms. So if you look at the attention maps for male and female, here male it is somewhat kind of distributed, for female it's somewhat focused. Okay, likewise for dark-skinned people and light-skinned people. So then we say, well, if this is maybe the attention maps are telling us that the network is looking at something so focused, and it kind of gets biased, it gets tripped. Okay, so we have another method that we are looking at now, where we try to keep the attention maps somewhat diffuse. Okay, well, when you do that, you are not biased, right? You are not just looking at a nose or mouth region and so on, which might create bias. But when you are diffusing it, then also what happens, the performance goes down. So you still have this issue trade-off. So when people say we want unbiased system, they never mention what they are worried about, whether they are worried about performance. As we say, there is no free lunch. Is there a bias-free system? Probably, but it takes a lot of care. Okay, so in terms of data curation, in terms of what the loss functions do, because when you have the loss functions, then you have the backpropagation algorithm, you have the attention maps. So you should go and check them out and make sure attention maps are not very different for the different, which is somewhat counterintuitive, right? We do want to distinguish the two different classes as much as we can, but we want to do them in a fair way, that we should, male to male, female to female, we want to be, the same way, right? So this is not a done deal. It has caught people's attention because sometimes things can go wrong when you let machines make decisions. And if you don't understand how machines make these decisions, we are going to have some, unfortunate situations. But for example, if a smart car, just goes and crashes somewhere, it becomes a big news, right? But there are like 40,000 people die in US due to car accidents. The number, goes up and down. But we say, oh my goodness, it's a sad thing. We got to do this. We got to do that. But when an autonomous car just goes and hits the lamppost, it becomes a big news. It's like dog biting a person is not a news, but if the person bites the dog, it becomes a news, right? So I'm not saying this is not important. It's very important. But you cannot just focus on bias reduction without paying attention to what happens to performance. So you need to look at that. Okay, the other example I want to show, which highlights another issue in AI, generalizability. Okay, so once you tell me, once I learn some concepts, then I go to a different place, I may be able to recognize them, right? Or something close to that. So if AI is so much bent on using data, and if the training data and the test data have different distributions, will the machine that we built using the training data work effectively on test data? This is not a new problem. It's an old problem. You can go and look at chapter 2 of Duda, Hart, and Stork, where we talk about building nonlinear classifiers or the kernel tricks in SVM. So generalizing across different data set is a well-known challenge, and there are many ways we try to address that, right? So in 2010, Berkeley group, Trevor Darrell and Kate Senko, they came with a problem. When they collected images of objects using different cameras, Amazon camera, DSLR, and webcam, when they trained on data using one camera and tested on the other camera, the performance went down. We looked at it a few years before that in the context of iris recognition, iris. So LG produced various sensors. So we trained our system using an older sensor and then tested on a newer sensor, a much better sensor, higher quality pictures, but the performance went down because machine learning was not used to seeing, better pictures, right? So we called it sensor adaptation. So here we were working on a transportation problem. Basically, we have traffic cameras everywhere in US and other countries. So we want to understand how much traffic is flowing, how many cars are waiting at an intersection, or is there any anomaly, that's happening? Somebody car, stopped working and they're parked on the side street. We want to know about it and so forth. So there are data challenges. Challenge workshops for this. They give us nice curated data. It's called UAD track data, city cam data, actual, camera, traffic cameras. I understand these cameras are also becoming deployed in India. Well, the thing is, the curated data set is a high quality data set, right? Now, if you go and apply your vehicle re-identification algorithm. Oh, I saw this vehicle here. Do I also see it somewhere else? Or you want to track a city scale a vehicle, a high valued vehicle, and so on. When you try to run these trained algorithms on actual traffic videos, because of the data shift, the performance goes down. So we have to look at what is known as domain adaptation. We have been working on it since 2010. We do unsupervised domain adaptation. We like it better. What does it mean? Source data is the data that you use to train your AI system. Target data is where it's going to be applied. And we know that they have different probabilistic distributions. So we want to understand how much shift is there in data. It's called covariance shift and so on. And then mitigate or mediate the domain shift. So we worked on manifolds from differential geometry, dictionaries from sparse representations. We also looked at generative adversarial networks and so on, right? So what we did here is that there is something that you all can also participate. AI City Challenge that we have been involved with folks at NVIDIA and many other organizations. Every computer vision pattern recognition conference since 2019 has been having this workshop where they give us these curated data sets and ask us to perform well in vehicle re-ID, vehicle counting, and so on. As you know, vehicle counting can become difficult if you are looking at vehicles that are far away from the camera because there's not enough pixels in them and so forth. So this is a clean, curated data. But then when we have traffic data, this is VDOT, it's Virginia Department of Transportation. And it has all kinds of issues, various scales, lower frame rate, compression effects, low resolution, 320 by 240, and so on. So what we have to do is to make, but for these data sets, we don't have any annotation. I can't go and run a detector on this. On the other hand, I have annotations for the curated data set because this was given as part of a challenge. Somebody put boxes around the vehicles and told us what these vehicles are and so forth, right? So I need to make sure that I have a way to adapt. So domain adaptation has become one of the hot areas right now in computer vision, machine learning, AI. Domain adaptation assumes the source and target data are available at the same time. There is a harder version of that in which we have worked on it, a number of others are working on it, domain generalization, where we only see the source data, never see target data. For example, Alexa, when it comes to your house, it has not seen your data, right? It has been trained on data, but has not seen yours. But there is an online training algorithm. Once in a while, somebody takes your voice data in Alexa, and then they try to fine tune it and so forth. So it gets better, okay? So anyway, so what we do is we adapt the curated problem to work on operational problem. This is like, there are two ways, right? I could make the operational data look pristine like the curated data. That's hard, super resolution, etc., etc. It's kind of hard. because the artifacts are there. On the other hand, I can dump down the pristine data and its annotations and then create, given the images, from the curate and pristine data and the operational data, we can make the curated data look like the operational data and then do the machine learning. So this is becoming very important. As you can see in these numbers, when we do these kinds of improvements, our performance goes up to 77, 75%. Whereas if you don't do it, it is in 37%, 36%. So if you don't do domain adaptation, you are going to be in trouble. So data shift is also important. Now in AI, why data shift is important? Because the performance will go down. So you need to be prepared. Now you may ask me, hey, if I don't know what the target data is, how do I do it? Well, what we do is we try to have multi-domain source data set, and then we use meta learning, learning to learn framework. And we have a 2018 paper on that at NURIP, so you can take a look at it. So how does it work? Well, buses are easy to get. They're big and bulky. That's good. But if you look at all these other little vehicles, we have numbers on them. We are confident of detections. As you can see, the data from highways, I-495 at US 29 is in Virginia. It's much harder than what you will see in a regular street and so forth. Okay, so this is important. Now, detection is important, but there's also re-identification. So this is the problem of, okay, I saw this vehicle here, can I see it somewhere else? What happens is re-ID, you cannot track because the pose is different. They've left one field of view and they're appearing in the other field of view. As you can see in the left blog, I again have domain adaptation, right? And then we go and, vehicle re-ID is a hard problem because vehicles look very similar. If you look at a Toyota Camry, kind of looks similar, but still there is subtle differences. So we developed a method called residual-based matching, which we discussed in ICCV 2019, ECCV 2020. And then we extract, key points and to estimate the orientation, so we can do a better job of identifying the vehicle and so forth. Now, one of the things we found is that our method, again, this has lots of blogs. What you will see here is we use GANs, okay, to do the domain shift, okay, across views and so forth. We actually use GANs to synthesize a generic vehicle picture and subtract it and look at the residuals. And then we see where the differences are. And we leverage that for doing the identification. Now, you will see the two blocks here, distance adjusted matrix. That's fine because, we don't want to have too much of the background. Same camera bias. See that I had to remove. Remember I told you, when you use data, the data is biased. Your algorithm is biased. So if I use only data from a single camera for doing something, then that, deep learning starts liking that particular camera. So you have to remove camera bias. And these details are described in our papers. But in any case, so as you can see, orientation bias also we have to remove. So we're not used to seeing the vehicle the same way. If you see the vehicle just from a side view all the time, obviously it's not going to work well when you see it from the front or the back. So you have to remove that bias. You have to remove the camera bias. So now in a vehicle re-identification problem, the bias is due to different reasons, right? Cameras, due to orientation and so on. In face recognition, the bias is because the gender is strongly expressed. What I'm saying is there is no universal set of things for which your system will be biased to. It is task dependent. You got to dig deep into it. You have to use GradCam. You have to use mutual information theory and so on to find out what is causing this bias. And then you go and do the bias mitigation scheme, okay? So the thing is, then you could do all of this and they put your results on the leaderboard. More than 100 systems have been submitted and we are in top 10. One of the things, what happens with these challenges, sometimes companies from different countries get very excited. They will put 20 engineers and tons of GPUs and hack the data like there is no tomorrow. And they usually are in the top few spots. Universities, we have a couple of graduate students working on it and so on. One of the new things that was introduced now is, given a language description, can I do it natural language, right? Suppose somebody says, can you find the red Toyota Camry, okay, and so forth. Yes, we can do that now. There is vision and language have always been kind of working together, sometimes, not sometimes, many times, etc. So these days we are able to bring more and more systems that work with both language and videos. It's important in many sense. It's useful for language-based inference, and it brings natural language and computer vision together, two core areas in AI. So there are things called BERT, VBERT, and CLIP, and so on. So we use to CLIP, basically we develop embeddings based on text, as you can see here, text encoder, image encoder, and then we will create the matrix made of dot products and use it for inference. So CLIP is the thing, and it again works well. And there are Alibaba. Alibaba, as you know, is a huge company, and they really do very well. And we are about 5% less than them, and so on. It's an ongoing project. So deep learning is useful for natural language processing, right? LSTMs and recurrent neural networks and so forth. So it's taken over. Anomaly detection is a problem where there is a stranded car, how you would go about doing that, and so on. So the last issue I want to talk about is protecting AI. When deep learning came, we were already excited. But then right around 2013, somebody said, okay, I add a little bit of structured noise to the image that you are using and see how it classifies. It created a havoc. Again, in time series, when you are working with the correlated stochastic processes, we know if you add a small amount of noise, it can give you bad results. Yeah, Doug Martin at University of Washington used to write papers on this in the late 70s. So it's like 3 sigma rule in Gaussian, right? Outlier detection and so on in robust statistics. So this is, the classifier, what it does is, clean image is lion, and if you add a little bit of noise, I'll tell you how much noise in the next view graph. It calls lion a pelican. That's not good. You don't want to mistake a lion to be a pelican. That's not good. Or a car to be a speedboat, a traffic light to be jeans. But you look, probability 0.97. That's very highly confident. It says, oh, that's jeans. You don't see jeans hanging around like that, right? Okay, so, and then you look at the difference, you see, the original lion and the attack image. They look very similar, visually indistinguishable, but for deep learning, one is lion, the other one is a pelican. Likewise, one is a car, the other one is a speedboat. One is a traffic signal, other one is jeans. And as you can see, the difference is minuscule. So, this created an issue, and then, lots of people got all excited, cybersecurity folks. So they came up with lots of different ways to attack deep learning. Just when deep learning was working, people say, let's attack. So the white box attacks, black box attacks. White box, you kind of know everything. Black box, you don't know a whole lot, but you can build surrogate networks by looking at input-output mappings and so forth. Anyway, so we got interested in it. We said, okay, let's do this. Suppose somebody, we train a network and somebody gives us a bad data, an adversarial data. We will project that data into the range of the training data set. Okay, so we built a GAN-based system. That's why it's called defense GAN. Okay, there's a very interesting paper, the Fuzzy brothers, adversarial vulnerability for any classifier. They showed that it's like, if you go out of your home, there is a small chance a car may hit you. Well, I mean, that may not look like a very profound theorem, but that's pretty much what it said, right? If you classify, there may be adversarial vulnerability, but different classifiers have different levels of vulnerability. So we basically build a GAN, and given the input image X, we will find a Z, and then when you put the Z through the generator, it gives an input that is very close to one of your training data sets, and therefore it will give good classification results. Okay, so how did it work? Well, those days we were all testing with MNIST data set. It's a OCR, optical character recognition data set. So in 2018, we had a paper in ICLR. And then 2018, ICML, Atelier, Carlini, and Wagner. Atelier was a student at MIT, Carlini is at Google, and Wagner is a professor at Berkeley. They tried to break all the algorithms that were presented in ICLR in April 2018, and they submitted a paper in 2018 in June. And that's remarkable, is it, in ICML? Because we put our code up in GitHub and so forth. As you can see, most algorithms, the performance went down to 0.9%, and ours 2018, Semengui survived 55%. But since then, people have been attacking defense GAN and so forth. But it is popular. It is what I call a generative approach for handling adversarial things. So it brought into our thinking things like manifold of training data, how you should be strong for deviations from on manifold data, off manifold data, and the whole work. So there's a lot of work going on. And then recently, we are also seeing object detector algorithms being attacked, right? So prediction on a clean image, the toilet, it works at 0.95, and then sink is, recognized. The moment you add some adversarial things, as you can see a little pattern there, so what we call a patch attack, okay, then it kind of goes down. Toilet goes to 0.8, it goes down to toilet, as they say, and so forth. So attacker can arbitrarily distort pixels within a region of bounded size and so on. So we built a way to segment the patch attack, and then we kind of complete it. It's called segment and complete. And then, we remove it, and then we do the detection and so forth. So this is an adversarial image, and then, we do a patch segmenter, etc., and then binary patch MAC and masked image, and then we do object detection. And this is, ongoing work. We have some, we tested it on MS COCO, right? That's a very classical object detection data set. As you can see, the patch sizes of various, sizes 75, 75, 100 by 100. The clean data set 49, and even when you have a patch size 125, 125, if it is clean, we are 49%. When you attack me, I'm 44%. So it's graceful degradation. Graceful degradation. One of my colleagues, former colleagues, who's now at UCI, Yasser Shukri, has a lot of examples of where a drone will be flying and suddenly will drop dead because he knows how to attack it. In the early days, they would say how they can attack an autonomous car, so it will kind of roll out of the road and things like that. So these are all interesting text cases, but our method seems to be working. Ground truth and prediction on a clean image, and then you patch attack, and D is we found the patch, and then we are able to. If the patch sits right on top of an object, tough luck, right? So that's one thing. But this is a cat and mouse game. This continues. We do better, and somebody attacks it, and then we try to do better. It goes on. But I do feel that most methods have these kinds of vulnerabilities. It's just that deep learning made it more sensational, to say. So here is a much more complicated aerial images with similar results. Okay, so we can detect various things despite having patch attacks on them. This is part of a DARPA program. So looking ahead, I think I'm getting close to my time. AI winter, I think AI is here to stay. The reason is because now almost everything we do is AI. If you go and ask any professor in computer science, are you doing AI? They say, yeah, of course, I'm doing AI. Okay, so how can such a broad thing, fail again? So AI is here to stay because we are continuing to collect data. I see the theme of this conference is AI and IoT and so on. IoT devices are very interesting. We all got excited and they're everywhere. They're also vulnerable. They're easy to attack because they're not very sophisticated, right? So it's like IoT creates its own business. It is there and it says, oh, I'm vulnerable, so why don't you work on me some more and make me strong, right? So definitely, when you are going to put an AI wrapper to do inference on IoTs, you are going to worry about attacks on IoTs. That's extremely important. So we need to consider designers either before we design or post hoc, right? So the bias issue is important. As I said, there are lots of metrics for fairness and so on, and it's not clear yet. They're task dependent. it's still, happening, research. Robustness is very important, and interpretability, it's we have lots of ideas on that, but it's again task dependent, right? So GradCam is there. I think what is emerging is human-centric AI. Human computer interaction is an established discipline in computer science. Robot computer human interaction has been looked at a lot, and AI and humans. For example, in the context of medicine, AI system, patient, and physician. It's a three-agent system. How would they interact, and who will have the upper hand, and so on. So I like to call it eternal spring for AI. So this is a good time to get into AI, and I wish you all very well in your academic endeavors and so on. I'm going to stop here, and I'm happy to take questions. Thank you very much for your attention.
Thank you, sir. This is Krishnamurthy from MCA department. My query is that you are telling that IoT devices are more vulnerable. But
yes,
the devices are almost hardware centric.
Yeah.
So how can the hardware centric devices become vulnerable?
Oh, I think you should look at, there are a lot of people who are working on hardware security. Professor Ankush Srivastava at University of Maryland, they call them Trojans, right? They introduce these things. If you're buying it from somewhere, they can plant little things. And in fact, a few years ago, Ankur was looking at the current profile, the current voltage profile of a normal system, an abnormal system, and so forth. So you are correct. Most emphasis is on software issues with deep learning, but the moment they start interacting directly with devices, your IoT devices at home and so on, somebody can attack the hardware. In fact, the example I showed you from Yasser Shukri, the software will be used to do something with the braking system or something, and so it will lose control. And things. There are a lot of examples of that. I'm not an expert on hardware, I'm more of an algorithm person, but it is of interest. Hardware security is of interest. When we buy components from other places, we got to be worried about it. Just like they can do adversarial attack on software, it's possible with hardware too.
Okay, sir. And is it possible so that I can implement that IoT in my private cloud? I can create a private cloud. So in that case, can I enhance the security?
Yeah, definitely. Yeah, all the cloud-based systems now are looking at that, right? They can provide better security. But, as I said, it's a cat and mouse game. Okay. I think I can never tell you that you're going to be 100% protected.
Thank you, Professor. Thank you. Thank you. Participants, you can unmute yourself and ask your questions. Sudha, madam.
Yes, sir. I'm there.
Yes, madam. Madam, you please further proceeding. Okay.
Okay, sir. I call upon Mr. Krishnamurthy, Assistant Professor, MCA Department, for proposing the vote of thanks.
Thank you, madam. A very warm evening for 1.5% here, and a warm day for the chief guest who has joined for today's International FDP session. On behalf of the management, I would like to express my sincere thanks to Professor Ramachellappa, Bloomberg Distinguished Professor, Departments of Biomedical Engineering and Electrical Computer Engineering, Writing School of Engineering, Johns Hopkins University, Baltimore, Maryland, USA. Professor, thank you so much for joining with us in a wonderful day. We are actually separated by 12 hours and so far. Thank you for delivering a wonderful speech. It is a fact that you have kept the audience spellbound, especially when you presented the result and discussion part of your research. That was fabulous. Once again, I extend my sincere thanks to the chief guest of today's function for accepting our invitation and presenting a wonderful session. Thank you, sir. Your presence and presentation added colors to the participants as well as for the organizers. Thank you, sir.
Thank you.
Thank you, sir. It's a pleasure for me to propose the vote of thanks. I thank our dynamic head of the department, Vice Principal Admin, Dr. Dileepan, for arranging this wonderful session. So 2 weeks International FDP. And I thank you, sir. Thank you for arranging this function. I thank all the participants who have joined from other institutions from India as well as abroad for making this function a grand success. I also thank my fellow colleagues for making this function a grand success. Once again, I extend my warm, sincere thanks to the chief guest and all the attendees. Thank you, Professor. Thank you all.
Have a good evening, everyone.
Thank you, Professor. Thank you, Professor. We will meet in the next event, sir. Okay. Thank you, sir. Thank you.
Thank you.
Thank you all. Thank you, all.
Thank you, sir. Thank you, sir.
Thank you, sir. Thank you, madam. Thank you.
Thank you,
Thank
sir.
you all.
Dear participants, the feedback link has been posted in the chat box.
Madam, and
Kindly
madam, please post the YouTube link also. Somebody
okay,
asking
sir.
the recording session. You please share our YouTube link also, so all the persons can view the sessions today. Okay.
Okay, sure, sir.
Thank you, madam. Thank you.
Okay, one more information. Tomorrow we will be joining around 10:30 for the next session. The session will be handled by Sheshwan from Malaysia. The topic is hybrid intelligence system, neuro-fuzzy expert system. We will meet tomorrow around 10:30. Thank you, participants. Participants, I had posted the YouTube link in the chat box. You can kindly make note of it.